Okay, here we go. We got no quizzes. We got review on Friday. We'll take a test on Monday. Homework tonight. Uh-oh. Why?
It's not a lot.
Because it's not a lot. Well, that can mean one of two things.
Or long.
Why would it be long if it's only four
No,
problems?
Because it'd be like A through Z.
Yes.
Yeah.
Right. So it's either going to be challenging or it's going to be there's only four problems there, but there's an A through Z or something like that for each one. It's neither. Okay. If you're okay with learning a process and the process has a lot of steps, none of them are challenging. As long as you're okay with that, then this isn't that bad. Yeah, most people would say this one's pretty bad. Right. I will try to convince you that it ain't that bad, but it's kind of bad.
So we're doing my father's day.
Tomorrow. All right. Yes, everybody good? All right, here we go. This is a two-part class. We get one part today. We'll get the main part of it tomorrow. Right. So recall from last class, we found that just like in the rectangular world where we have diagonal lines, we have vertical, we have horizontal lines, the same thing happens in the polar world, plus a few weird things. So the weird things in the polar world is that sometimes we get circles instead of diagonal lines. So R equals whatever that number is a circle centered at 0, 0. Theta equals is a diagonal line. And then we get our straight up vertical horizontal lines. We're just talking about that example where R cosine theta is equal to a vertical line and R sine theta is equal to a horizontal line. And then the last thing, here's an example of both. And then the last thing is that sometimes we get a circle that isn't centered at 0, 0, and that will be in this form. It'll start off with R equals, and then you're going to have either a 2 or a -2, and then you're going to have a number, and then you're going to have either sine or cosine. If it's sine, it's of the form 0, a or 0, -a. It'd be -a if there's a -2 involved. And then the form, if it's cosine, is a, 0 or -a, 0, depending upon whether you factored out a 2 or a -2. And that was your homework. All right, cool. Now, example of both. Today, we're going to be doing the first weird shape. All right, between today and tomorrow we'll get this shape right here. We're doing some awfully strange shapes. Not a circle, not a diagonal line, not a horizontal, not a vertical line. I don't even know what the heck that thing is. We will know what this is tomorrow. But for right now, it's just a weird looking shape, right? Some weird things. By the way, this does not exist in the rectangular world because that's not a function. So in the polar world, this idea of function is changed. We can pass the vertical line test in the polar world and still be a polar function. Okay. So it turns out that in the polar world, lots of weird shapes, lots and lots and lots of weird shapes. They are extremely hard to graph by hand, right? Can you imagine graphing this by hand? Yes, no?
No.
Guess what tonight's homework is?
That.
Graph this by hand. Okay, so you're going to be graphing something like this by hand, right? How many points would you need to make this shape? You could graph that shape with 3 dots and play connect the dots and make that shape. So 6.
Oh, 6, yeah.
So you're saying you could make this shape with 6 points. You guys agree? Disagree? I need to reproduce this shape. She says that she can do it with 6 dots. How many?
9 is bare minimum.
She's saying 9, but will we agree that it's more than 2? So when we graph lines, all we ever need is 2 points, play connect the dots. With a circle, you really only need a radius and a center. So 2 points again, or two values. How about that? But with these weird shapes, you need a bunch. So why are there only 4 problems tonight for homework? Because you've got to graph a lot of points. I would argue it's probably even more that you're doing some guesstimation when you play connect the dots if you only do 9 or 10 points. Okay, so it turns out that they are hard to graph by hand. Some of the shapes have a special unique feature that will make our life easy, and you guys kind of already figured it out. What's unique about this shape that actually makes your life easier? What do you mean by the same? She says the top part is kind of like the bottom part. What's the fancy word for that? Symmetrical, symmetry. And we've seen this in the rectangular world. We had, let's see, we had x-axis symmetry, we had y-axis symmetry, we had pole symmetry. Guess what happens in the pole world? Or origin symmetry, sorry. Guess what happens for the polar world? We get the same thing, they just have different names. We can't call it x-axis symmetry because we don't have an x-axis, right? So even though this looks like it has x-axis symmetry, remember what I said, that the rectangular coordinate system lays upon this perfectly fine. I guess we could say it has x-axis symmetry if we consider it to be a rectangular shape, but it's a polar shape. So we need a name for this blue dotted line. What? This is going to be polar axis symmetry, right? We have a different one called pole symmetry, and I'll just say that that's another reason why this is a bit more challenging because of this word pole symmetry and polar axis symmetry. Polar axis symmetry means this. Look, it's symmetrical about the, well, I'll use the word x-axis, even though we're talking about the polar axis, right? So this idea of symmetry, that means you got a mirror image, right? There's some line that you can draw through the shape where the left side equals the right side or the top equals the bottom, that sort of thing, right? So what? Well, it makes your life easier. So if an equation has symmetry, you only need to graph half of the points and then apply it to the other side, right? What are you doing? What did you pass out? Boy, wouldn't it be nice if we were back in Algebra 1? Well,
No.
okay, so polar axis symmetry. So the rest of today and into tomorrow's class, it's just one thing, and that is graphing these very strange shapes, but using symmetry to make our life easier. I will be introducing you to 5 weird shapes. Seth, you gonna make it? I'll be introducing you to 5 weird shapes. Today, you only get one of them, right? You're going to graph each, but you're going to be graphing them by hand. You will be using symmetry to make your life a little bit easier, right? There are 3 basic symmetries. We also call them tests. And so you'll be seeing if they're symmetrical to start with. And then you will be doing, you'll be doing a test for symmetry, one for each. There's 3 of them. Then once you determine how it's symmetrical, you will be using a shortened table of pain, unfortunately. That's our 6 to 9 points, okay? And then we will, from that, get a duplicate 6 to 9 points from that reduced table of pain. It's not short, right? It's a long process, right? You apply the symmetry, now you have double the points, and the shape will emerge. So the next 2 days, these green little boxes right here are what we're going to do. We'll test for symmetry, we'll do a shortened table of pain, we'll graph those points, and then we'll apply that symmetry and get double the points. All right, so what are those symmetries? All right, so in box number 1, there's an A, B, and a C. We will be writing each one of those symmetry. Well, let me do the slide first, and you copy it down. All right, so let's think this through, right? If there is the top of the blue line, that the only difference between it and the bottom blue line is that what's negative?
The Y values.
Not the Y values, because remember we're the theta, right? So the only difference is the theta on the top above the, well, I'm not going to say x-axis. It's not the x-axis. It's the polar axis. Above the polar axis, theta is positive. Below the polar axis, theta is negative. So the only difference between, remember, the blue is the entire shape, right? It's this V-looking thing right here. But it has symmetry about the polar axis. So the only difference is one is theta, one's negative theta. Well, then that simply means is that, well, they both give you exactly the same equation, theta or negative theta. So if you replace theta with negative theta, you should get back to the same equation. That's going to be our test for symmetry. We'll write down here in a second. So if this results in the same equation, then you conclude that it has polar axis symmetry. Yes, in parentheses, I put x-axis symmetry. There is no x-axis, but Come on, we probably all think about this as x-axis symmetry. All right, write this down. Red is the key part. So if you're testing for symmetry with respect to the polar axis, this is going to be confusing because we're going to get one for just the word polar. So this is polar axis. Then you replace theta with negative theta, and if that results in the same equation, then you conclude, yes, I have polar axis symmetry. We'll do an example of this. You'll see it here in just a second. There are 3 tests for symmetry. This is symmetry test number 1. See if it has polar axis symmetry. If you want to think about this as x-axis symmetry, you can. It's just no x-axis on the polar coordinate system. Okay? The next one. Yes, many people think about this as y-axis symmetry, but there's no y-axis. There's a pi over 2, though. That would be where the y-axis is the rectangular world. So if you think this through, right, I'm looking at imagining there being a y-axis right here, or pi over 2. I've got the little blue line there on the right of that. That would be the angle theta. So if it's symmetrical about pi over 2, then this angle would also be theta, but the real angle there would be 180 minus theta. In other words, pi minus theta. You see what they're saying here? The part on the right, which is theta, the part on the left, which is, well, it's unnamed, but to get to that, that would be pi minus theta. So in other words, if it has that, then if you throw in pi minus theta and you get back to the same equation, then it has, we call it pi over 2 symmetry. Right? Remember, vertical lines are of the form of theta equals, or I should say, lines in general of the form theta equals. That's why it's not r equals. R equals will give you a circle. Okay, so write this one down. And yes, if you want to think about this as y-axis symmetry, you can, but it's more formally called with respect to theta is equal to pi over 2. So the first one will replace theta with negative theta. The second one is pi minus theta. And then the last one, right? In the rectangular world, we would call this origin symmetry. Well, we have no origin, but we do have a pole, which is why this is called with respect to the pole. And this is, as Leek was saying, it's confusing because one is polar axis and one is pole. So pole means that it looks like if you turn it 180 degrees, you get, or if you turn it 180 degrees or less, you get back to exactly the same shape. So if this black angle right here for the one above the polar axis is theta, to get to the other portion of it, right, it would be theta plus pi, which further confused. The previous one was pi minus theta. This one is theta plus pi. Same idea. If you throw in theta plus pi and you get back to the original equation, then it has what's called pole symmetry. All right. So if you replace theta with theta plus pi and you get back to the original equation, then it has pole symmetry. The way I remember this, in this specific order, if you look at what you're replacing with it, replace it with theta, pi, theta. And then it goes minus plus. First one everybody gets and remembers x-axis, then y-axis, and then it's not origin, it's not either x or y either, but you get the idea. Most people have to have this written down on a resource card. They're not going to remember this. So these are the 3 tests for symmetry. Everybody okay? All right. So great, you know symmetry, what do you do? So remember, once you test for symmetry, then you do a reduced table of pain. So what values will you use? And we'll do them one at a time. All of these are going to go into box 2. So you're going to have 3 tables in there, right? In box 2. These are going to be the parent tables to do this. Now I'm going to apologize up front. We think of an ordered pair as XY, or the polar world as R theta. Theta is going to be our input. So I'm going to write you the table backwards. Instead of the table being R theta, it's going to be theta R, because R is what we're going to be solving for. All right, think about this shape right here. All right. If this is symmetrical, it's symmetrical about the polar axis, then I only care about the top or the bottom. Pick one. So if you pick the top, then I simply need to graph the top. What's above my hand? What degrees or what radians are above my hand? So what values? No. What theta values are above my hand? You said, let's not worry about the bottom. Let's just deal with the top. 0 through pi. So we want all those unit circle values from 0 to pi. That's my reduced table of values. So for polar axis symmetry, all you need is the values 0 to 180 for theta, not for R, but for theta. So once again, the table should go R theta. I'm going to give it to you theta R. So there's my table right here in black. Write that down. Notice I skipped 45 degrees. So we got 0, 30, 60, 90, 120, 150, 180. That seems like an appropriate number of values. We get 1, 2, 3, 4, 5, 6, 7. Priscilla said, let's use 6. She said, let's use 9. Well, if we think about this as symmetrical, we get double this. So this is going to give us 14 total points if we think about the symmetry. It's going to give us 7 points from the table, but we'll get an additional 7 from the symmetry. Now, let me briefly talk about what you're going to do with the symmetry, okay? So we're going to graph the top above my hand right there. We'll graph the top above the 0 to 180. We graph it. We're going to graph it, how many points it gives us. How do we get to the points on the bottom now? What do we do to get to the points on the bottom? We just make theta negative, and that gives us our other points. If you want to think about it instead in the rectangle world is, if it has x-axis symmetry, then all you do is you take a point and you make the y negative. It's the same idea. The only difference here is that the y value right here is theta. And yes, my table is backwards. Hopefully you can wrap your head around that. Is that confusing to anybody? Like I did the table backwards? Like it should go R theta, not theta R. This says the word equation because where do you get the R value? You're going to get the R value by tossing in theta into the equation, and that spits out an R value. We'll do an example. Don't panic yet. All right. How many of these tables we're going to have? There's 3 symmetries. We're going to have 3 of these. All right. Ready to go on? All right. So this is going to be our y-axis, except it's not called y-axis. It's called pi over 2 symmetry. So this is our pi over 2. So I'm going to cover up the right or the left side, your choice. I'm going to cover up the left side. So what angles is that? Give me all the angles on the right side. Give me all the angles on the right side of my hand. 3 pi over 2 is over here. That's where my left hand or my hand's covering up. So it's not 3 pi over 2. Well, what's on the right of my hand? Okay, now you got this part. What's this part? If you say 3 pi over 2, we're going in that direction past my hand. I just want from here to here, which is what? Yeah, but 7 pi over 4 is including that. I don't want to go there because I'm covering that up with my hand. I just want here to here. You're overthinking this. What's the restriction on sine? How about we go with that instead? -90 to +90, right? So I need all those values for my table for theta between -90 to +90. So -pi/2, -pi/3, -pi/6, 0, pi/6, pi/3, pi/2. Once again, I'm skipping the pi/4. Why are we skipping, or why are we doing this? We could easily put it in there, and you can. It'll just give you an extra point. If we think about in terms of, I don't know, equally distributed from left to right, pi/4 is 45 degrees, so it's halfway between 30 and 60. But you don't get a halfway between 60 and 90. So to me, it seems like if you're going to use 45, well, then you also need to do halfway between 60 and 90, 75. And since 75 is not on the unit circle, I just call this a happy medium. But you absolutely positively can throw that pi/4 and -pi/4 in there if you'd like. So that would give you 9 points or 18 total with the symmetry. Okay. Tell me what you're going to do once you find your point on the right. How do you get to the point on the left? You make theta, right? The x value, right? In this case, the x value is actually this value right here. So you're going to take pi 180 and you're going to subtract pi from it. I said that completely wrong. You're going to take pi, you're going to subtract theta from it. There we go. Yikes. And that's how you get your new theta. And the reason that you don't think about in a rectangular world, you'd make the x value negative. We don't want to make r negative. We want to keep r whatever sign it was. So we're actually going to change the theta value. So to find the symmetry here, you're going to take your whatever your theta was on the right, and you're going to subtract that from pi. That will give you a new angle to apply to, and that will make your symmetry. Good? We've got one left. All right, origin symmetry. So for origin symmetry right here, once again, well, this time we are going to, in fact, make r negative, right? But for the theta, we're going to do theta plus pi. So my values are going to be, we can do top or bottom at your choice. I just always choose the top. So 0 to 180. So this one's going to look just like polar axis symmetry. The table of pain will look just like, so it's going to be 0 to 180. When you put that stuff in your hair, do you do it by hand, or is there a device you use?
The tinsel?
Yeah.
They can put string, like the tinsel, and she makes a knot. Basically.
She ties a knot to your hair with the tinsel. So when you get tired of it, what do you do? That's what I thought. That's literally was my question right there.
I thought this in for so long, but
Well, when you brush your hair, doesn't it just come out?
sometimes it does, like, if like my hair is like real like natty, then it'll come out. But it usually doesn't come out.
These are conversations that guys never have. We miss out on so much.
Yeah.
It would have to be a short piece of tinsel.
Yeah, hot pink.
Thinking no. I'm thinking
Red?
no.
You could match your test.
Yeah, it's red though.
Yeah. So red.
Ink doesn't match
No,
red.
no, it said red.
You said pink to start with.
No.
But yeah, but then she was like, oh, or what, then she changed it
Okay.
to like.
It'd be cool.
Yeah. All right. I get a feeling that there'll be some people confused at this point, so we better do an example. So remember what the procedure was. You do each test, you figure out which symmetry it has, then you, if it does, and it will tonight for homework and tomorrow, when it does have that symmetry, you use that shortened table of pain to find the other values, right? And then you apply the symmetry. Okay, we will do one example today. It's going to take us, 15 minutes to do one example, right? Hopefully it's a little bit quicker when you do it tonight for homework, but it'll certainly take 15 minutes to do one example. So why are we doing this? Remember, if you don't do this, you don't even know what the shape is. So if you don't know that it has symmetry, then you would literally have to graph hundreds of points for the shape to emerge. So this is much easier doing it by hand. Who's this actress?
She's from Maze.
Right.
Or grown-ups.
Nope,
Yeah.
never seen it. I know she's an actress, but
You've never
Watched both
seen
of those
Grown-Ups?
movies.
no,
Do you watch TV?
no, I watch YouTube.
YouTube Shorts.
A lot of that.
Okay.
And then my wife says, "What are you doing? Get a life." All right, here we go. We're gonna do one. All right. Happy Valentine's Day.
Is it
It's gonna be a
because
heart.
it's a heart?
We'll see. Hey, notice from its shape, do we have this form yet? We've had r sine theta, we've had r equals sine theta. Have we had anything that look like this?
If you move
Oh.
the line. Oh, just
Did we have anything with a plus or a minus? No, not yet. So this one's new. Okay, so the procedure is tonight for homework, they're gonna give you an equation, it'll be polar, and they're gonna ask you to graph it by hand. Step number one is the 3 tests for symmetry. It doesn't matter the order that you do them in, but I'm gonna do the order that I gave you. What was the first test for symmetry? So I replace theta with negative theta, and I see if I get back to the same thing. So I'm gonna replace theta with negative theta and see if we get back to that equation there in red.
Wouldn't it not because it's, odd
It's an odd function, so the negative goes to the front, and so that negative would turn into, so it'd be 1 plus sign, and that ain't 1 minus sign. Okay, so it doesn't have polar axis symmetry. What's the next test? So we gotta replace theta with pi mi-. Yeah, it is. What did you write?
Wait.
Second one. Pi over 2 symmetry. Pi over 2 symmetry. What did you write? What did we replace?
Theta with pi over 2.
No.
What?
So if it has pi over 2, we're supposed to replace theta with pi minus theta. Make sure you change that. And now we got a big problem because I don't know what to do. Well, I do know what to do, but I'm playing it up. Anybody see anything?
Would you do would you like make it? Would you do what you did to the last problem, but then would you?
I can't because there's 2 things on the inside. When there's only one thing, yeah, I could do what I did before, but there's 2 things on the inside. And I don't know what theta is.
Are we gonna use the half angle one?
Very close, but it's not gonna be the half angle, it's gonna be the,
Double angle.
not the double, it doesn't say 2. If only we had an identity where you had 2 things subtracted from each other. And what's that called? Well, you can be smart too if you simply open up the back of your book. If only we had an identity where you had the word sine and you had 2 things on the inside with a subtraction symbol.
Sounds like the half angle thing.
It's not the half angle. It's not theta divided by 2. That's the half angle. Do we have something that says sine and then you have something minus something? Which one is it?
Oh, sorry. The sum and difference.
The sum and difference one. This one's going to be the.
A minus.
Difference, alpha minus beta. All right, so give me what I'm supposed to write.
Sine A cosine.
Keep talking.
Oh, cosine A cosine B minus sine B cosine A.
I don't think you said that right.
I flipped up.
Right. I think it's sine, cosine, cosine, sine, am I
Yep.
right?
Yep.
All right, so it's sine, cosine, cosine, sine, whatever this sine is goes right here. See what I did? We got alpha, beta, so it goes alpha, beta, alpha, beta. You see what I did? Well, that's convenient because what's the sine of pi?
0.
Sine of pi is 0. Sine is what? X or y?
Wait, yes, 0.
Sine is
Y.
y. What's y at pi?
0.
0, right? That's convenient. That means that whole thing goes away. What's the cosine of pi though?
1, -1.
-1. You see what I did? I replace sine pi with 0, replace cosine pi with -1. Well, 0 times cosine theta is just 0, so you're left with 1 sine theta, but I still have this negative on the outside, so these two negatives right here are going to turn positive, but I still have this negative on the outside.
Okay, negative.
So it's going to turn into that. Is that the same as this?
Yeah.
So therefore it does have pi over 2 symmetry. By the way, every time you do this test for symmetry, guess what you're going to have every single time? You're going to have a difference, right? It's always going to be, either sine or cosine or the tangent. You're always going to have a difference because you're always throwing in pi minus theta. So it's always going to be one of those of the 3 difference formulas.
So is the next one you did before?
Well, let's see. What's the next test? Pole symmetry, or symmetry with respect to the pole. And what are we supposed to replace theta with?
Plus 5.
Theta plus pi. These are hard to remember, right? So we replace theta with theta plus pi. And that's the difference, or that's the sum formula now. Sum formula, the only difference for sine is somebody, anybody?
Wait, what? Oh, sine alpha cosine beta plus sine.
When it changes the plus symbol, okay? So for sine, it's always sine, cosine, cosine, sine. Cosine is not like that, right? Tonight for homework, you might have a cosine one. So we get that right here. That's convenient. We already said cosine pi is,
Negative.
and we said sine pi was 0. So that part goes away. Sine is an even odd function, so the negative goes to the outside. You already got a negative there, so it turns positive. Therefore, it's not the same. So as soon as you understand it's not the same, you don't have to continue.
Well, if we have line, then should we assume that we don't have?
You got to be careful because it depends upon the shape. A circle centered at 0, 0 will have all symmetries. So you can have one symmetry, you can have no symmetry, you can have multiple symmetries. In this case, we only have one symmetry, and that's pi over 2 symmetry. I got an odd function sine of negative, I'm sorry, not an odd function. Why did I say odd function? The negative one's on the outside. It still turns to positive though. Ignore what I said about the odd function. That's not odd. If theta had been negative, then it would have been an odd function. I got ahead of myself there. Poor use of parentheses here. I should have put that theta in parentheses. All right, we okay? All right. So it feels like we're done, but we're a third of the way through. Now we have to do table of pain. So look at your box 2. What's the table of pain for pi over 2? Yeah. So we're now on step 2 of 3 steps, right? So we need the table of pain, reduced one, for pi over 2 symmetry that you wrote in box 2. And if you didn't label them, then label them now. The first one is polar axis symmetry. The second one is pi over 2. And the last one's with respect to the pole. So what's the pi over 2 one? -90 to +90, right?
Oh.
Correct? Okay. So remember, these are the 3. For your x-axis symmetry, this was the table of pain. For the y-axis symmetry, this was the table of pain, -90 to +90. And then lastly, with respect to the pole, this was your table of pain. Okay. All right. So we have this is the one. No, I was showing you all 3, and now I'm showing you one. Okay. Remember the table's backwards. Instead of being r theta, it's theta r, but it's fine. Remember, when we graph for polar, we do graph theta r anyway. So there's my equation. We just need to throw those values in. All right, grab your calculators. make sure they're in radians because we're throwing in, or change those to degrees if you want to leave it in degrees. All right, do the first one. Let theta be negative pi over 2. It's going to be a decimal number or a whole number. What do we get?
Wait, how many times is it?
Literally, you're going to do 1 minus sine theta, except theta is going to be negative pi over 2. Are you sure you're in radians? So once again, calculator's not your friend, and it will not tell you that you're getting the wrong answers.
2.
She got 2. What'd you guys get? Nick's saying 2. And Seth's saying 1.02. Now always gets 2. Okay, so it's 2. All right. Negative pi over 3. Leave, you know what we're doing?
1.86.
Do the calculated part by another again.
Okay. But you understand how we're getting these numbers?
Yeah.
Okay. All right. Is that about enough? I can show you the answers for the rest. I want you to write them down just so you have this, but just remember, for the sake of time, I'll just give you, all we're doing is a calculator drill here. We're getting all these values. Okay. Copy those values down just so you get the process. Okay. We're 2/3 the way. What's the last third? We got to graph this. How many points are we graphing? 14. Here's 7. Where do we get the other 7 from? And it has pi over 2 symmetry. What do you change to get to the other side? You change theta. You can do this visually as well. All right, so let's see. How do we graph this? We got to go to negative pi over 2. That's straight down. And then we go to the value 2. So here's 0. Sorry, here's negative pi over 2 straight down. And here's the value 2. Yes? Here's the radial negative pi over 3 and the value 1.87. Here's negative pi over 6 and 1.5. And so forth and so on. All the way up to pi over 2 and 0, which is the origin. And that's how much of the graph? That's half. So we got to take each one of those dots and reflect it to the other side. You can do this with your eyeballs, right? You don't have to throw in pi minus theta, right? So we can, well, there's no reflection from the center dot. This dot would appear right here, right? This dot would appear right here. This dot would appear right here. This dot would appear right here. This dot would appear right here, and that dot would appear right there. Now play connect the dots, and you get, yay, there's half of the heart, and the other heart would be right there. So happy Valentine. Usually this class is right around Valentine's Day, so. Yeah? Kind of cool. A lot of people say it looks more like an apple than a heart. I get that too. A peach? Okay. All right, guess what? This has a name. Guess what it's called? Heart just doesn't sound too mathy. Is there a more scientific word for heart? All right, we call these, write these down next box, we call these cardioids. Because somebody like, we can't call it heart. All cardioids are in this formula right here.
But they're just hating.
They're what?
They're hating
They're hating
on heart.
on heart, right?
You can't call it a heart.
All right. Notice our previous one said 1 minus sine theta, right? So in front of the word sine theta would have been another 1. So if you want to make another heart, then you can make 2 minus 2 sine theta, or 2 plus 2 sine theta. Or you could write 3 plus 3 cosine theta, or 3 minus 3 cosine theta. It says that first A has to be greater than 0. Once you're done writing this down, grab your calculators. Priscilla, give me a number.
Oh,
12,
no, just kidding.
2. So I want you to graph 2 plus 2 sine, no, 2 minus, because we want it to look like a heart. 2 minus 2 sine theta. All right, graph that on your, make sure you're in polar form. Do 2 minus 2 sine theta. And as long as you are in polar form, you should get a heart. You may have to do a zoom in. What is going on with your calculator? Are you in polar? All right.
I got an oval.
He got his heart.
I got an oval.
Mode. See where it says pole? Now notice it doesn't say y equals, it says r equals. Hit zoom in once. So do 2 minus 2 sine theta.
What is theta?
It's the x value. You notice the x button.
What's the brightness of
I hit
it?
zoom square first. Square is number 5. And that'll make your screen a square instead of a rectangle. And now hit zoom in once.
It's still an
Enter.
oval.
Yay! There you go.
It's still an oval.
All right. Where did you, what's the problem?
It's still an oval.
Yeah.
Did you use the negative key or the minus key? That's why.
No, I did. I was trying to do something with it and you weren't catching on.
There we go.
It's too late now.
Definitely not a heart.
Then you're in y equals, put it in polar form. Oh, polar. Now, y equals 2 minus 2 sine theta. You put x,
Yeah, that's what you literally told me. I asked what theta was.
it's just
Use
the x button. See what it says xt theta n? There you go. It knows that you're gonna. All right, hit zoom standard or square, sorry, zoom square. Make it a square and then hit zoom out. Zoom out. You're really zoomed in. Enter again, enter again.
Oh, enter?
Yeah.
Just keep hitting enter.
No. Zoom out, enter,
Zoom.
enter. Zoom out, enter.
30 seconds?
Oh my God.
Are you sure?
Oh, that's not.
Now you can zoom out. All right. Hey, what do you think the A value does? We just did 2 minus 2 sine theta. What do you think the A value does? Well, we can figure it out. Let's do another one and let's let A be. It is 2. That's the one you just entered in. Let's make it be 4. So this time do 4 minus 4 sine theta. See what you get.
A bigger heart.
Okay, so what does A mean?
The
What does A represent?
the X.
The width? No, A represents how much you love someone.
The scale.
No, represents how much love you have.
I mean, like the scale, like how.
Okay, you go with scale, I'm going with love. Well, then your A value is 0. And therefore, you get a dot right at the center. You don't even get a heart. All right, obviously that was a joke, right? What does the cosine do? Well, let's see.
It's your life.
Just remember the A values have to be the same. So what does it do? It turns it sideways, rotates it 90 degrees. Is that what you got? That one?
That's
Is that what you got? A rotation of 90 degrees? Yeah, okay. All right. Hey, that sounds about it for today. All right. There's only 4 because it's a long process. You got to test for symmetry, Then you gotta apply your symmetries to a reduced table of pain. By the way, how long does it take for you to check? How long does it take you to check? You literally typed in 1 minus sine theta once we figured out our calculators, and you got the answer very quickly. So yes, doing it with technology is way quicker than doing it by hand, but you now know the technique to do it by hand.
Can you print these?
Can I do what?
These?
The more of those?
Yeah.
Yeah, can you print some for me too?
I can.
How many people have came up to you today to use your printer?
Nobody.
Nobody?
No one has asked. Oh, from teachers, most teachers, when they go home, they, before the weekend, they get their printing done out of the way. But on a Tuesday, that's a different story. No.
Oh.
Right. On a Monday, most teachers already have it done.